This is the video for the 9.1 LOpps out of the textbook, these problems. I need to tell you 79 is harder than anything I would ever give you. It's something that we ought to only look at just for something to be interested in. So that's what I have to say about that before we get started. Okay, the first problem, number 23. It is on the graphing calculator. So my equation is 16 times negative 1/2 to the n minus 1. And we are going to look at this on the window of x being from negative 1 to 12 and y being from negative 10 to 10. So if I go to my window, x negative 1 to 12, y negative 10 to 10. Okay, and going back to my y equals, I like to look at my style. I like these in little squares. You can do dots, but squares are better because you can see them. All right, so let's look at the graph. Okay, look at what is happening. My sequence. Okay, so we get the nth term going to 0. Number 33. We want to know what this sequence looks like, so we've got to get skilled in simplifying our factorial functions. So n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, and so forth. So we could actually just simplify this as n plus 1 times n factorial over n factorial. These cancel, leaving n plus 1. 35, again, simplifying this, 2n minus 1 factorial over 2n plus 1 factorial. To simplify a factorial, we have to take the greater one and reduce it down to this one. So I would take 2 times n plus 1 times, subtracting 1 from that would leave 2n, times, subtracting 1 from that would be 2n minus 1 factorial. I could keep going, but it allows me to cancel these, and we get 1 over 2n times 2n plus 1, and you can leave it like that. So 37, we're asked to take the limit as n goes to infinity of 5n squared over n squared plus 2. These follow our exponent rule. Same exponent, ratio of the leading coefficient. So my limit is 5. 39. So here we have is an n under a radical. So we have to remember how to simplify this. We're going to divide by n squared underneath a square root. So what happens when I divide this by the square root of n squared? Notice that n is going to positive infinity. So as n is going to positive infinity, the square root of n squared is going to positive n. So this becomes 2n divided by n. Under the radical, I'm going to divide every term under the radical by n squared. We can simplify this, and we can see that as we go to infinity, we go to 2 over 1, because this term would go to 0, which is 2. So for 45, again, we're going to put this one on the graphing calculator. X is going to go from negative 1 to 12. Y is going to go from negative 2 to 2. I've already entered this one, so I'm going to turn off that function and come down here and turn this one on. Going to go change my window. Same X. Y is going to go from negative 2 to 2. Let's see what these terms of the sequence do. Again, I can trace. There's where n is 1, n is 2, 3, 4, 5, and so forth. Notice that we're going from 0 to negative 1 to 0 to 1 to 0 to negative 1 to 0 to 1. So this is the terms of our sequence. So the limit as n goes to infinity of our sequence does not exist, because let's remember, as n goes from 1 to infinity. When n is 1, I have cosine of pi over 2, which is 0. When n is 2, I have cosine of pi, which is negative 1. When n is 3, I have cosine of 3 pi over 2, which is 0. When n is 4, I have cosine of 2 pi, which is 1, and so forth. So our limit does not exist. 47, we want to find the limit as n goes to infinity. So listing the terms of our sequence, when n is 0, I get 1 times 0. When n is 1, I get a negative 1 times 1/2. When n is 2, I get 1 times 2/3, and so forth. So here's our general term. As n goes to infinity, our sequence oscillates between negative 1 and 1, and it's getting closer to 1 and negative 1 with each term. So a sub n diverges. Again, we can use our exponent rule. As n goes to infinity, I have the same degree, so it's the ratio of the leading coefficient. So an, my nth term, converges, my sequence converges. Number 59, again, we've got to simplify our factorial. Notice that n plus 1 factorial would be n plus 1 times n factorial. Now that I have n factorial on the top and the bottom, I can cancel those factors, and I get the limit as n goes to infinity of n plus 1, which is infinity. So my sequence diverges. Okay, 61. Limit as n goes to infinity of n minus 1 over n minus n over n minus 1 for all values of n greater than 2. You understand why n cannot be 1. Okay, so n greater than or equal to 2. Let's get common denominator, this product minus this product over this one, which becomes this. The n squareds are going to cancel each other out in the numerator. So in the numerator, I actually get 1 minus 2n on top. I get n squared minus n, bigger exponent on bottom. The limit of the nth term is 0, so an converges. All right, 63. Limit as n goes to infinity of n to the p over e to the n. Now, we have to think about what's going on. Is our numerator getting bigger faster than our denominator, or is our denominator getting bigger faster than the numerator? Well, right now we know that the limit as n goes to infinity of n to the p would go to infinity. The limit as n goes to infinity of e to the n would go to infinity. So we have a L'Hopital's rule situation. We're in indeterminate form, okay, and L'Hopital's rule will apply. We also know that p is a number greater than 0. Now, what's going to happen is when I take the derivative, I'm going to get p times n to the p minus 1 over e to the n. And I'm going to continue to get derivatives. I'm going to continue to have indeterminate form until I finally get the limit as n goes to infinity of p over e to the n. Again, p is just a number. It's a constant. So finally, I get the limit as n goes to infinity of p over e to the n, and that's going to go to 0, so my sequence converges. 65, we have this going on. Now, this looks suspiciously almost like that limit as n goes to infinity of 1 plus 1 over n to the n. So let's do a little work here. We can let u equal k over n, which makes n equal to k over u. As n goes to infinity, u would go to 0. And now I can do my substitution. I'm going to let the limit as n goes to infinity of 1 plus k over n to the n be the limit as u goes to 0 of 1 plus u to the k over u. So this expression right here will become the limit as u goes to 0 of 1 plus u to the 1 over u, all raised to the k power. And let us remember our limit rules. I can take the limit of this expression and raise it to the k power. Well, this right here, you need to recognize is a form of e. So we're looking at e to the k. So when u is k over n, a sub n, or my sequence, converges. Okay, let's look at 67. As n goes to infinity, sine n over n. Now, this is not the limit as n goes to 0 of sine n over n. We have a theorem for that. That is not what this is. But we could rewrite this expression and think about this as the limit as n goes to infinity of sine of n times 1 over n. What we know is that that is bounded between negative 1 and 1. And as n goes to infinity, this will be 0. So my limit is 0. So my sequence converges because we know that sign of n is bounded by -1 and 1. 75, we're supposed to come up with a sequence that this models. Okay, this looks like 1 plus 1/2, 1 plus 1/3, 1 plus 1/4. So how do I get 2 here? Well, that would be 1 plus 1/1. So this looks like it is the sequence. A sub n is 1 plus 1/n. 77 looks like on top when n is 1, 2, 3, 4, 5. So it looks like the numerator is n. The denominator, that looks like, well, this is when n is 1, so that's n plus 1 times n plus 2. Let's look at here. When n is 2, n plus 1 times n plus 2. All right, there is your pattern. 79, I will never give you one this hard. We have 2 times n trickery. So here is your sequence. And this is where n is 1, n is 2, n is 3, n is 4. You'll notice that the denominator has all odd numbers in it. You'll notice that we have alternating signs, so that's going to be important. That means we're going to have a -1 to some power. It looks like it's going to be n minus 1, because here, when n is 2, I have the term to be negative. So that would mean my exponent on the -1 needs to be n minus 1. When I get over here to the third term, 3 minus 1 would be 2, and a -1 squared would give me a positive number. So let's consider what 2n factorial would mean. That would mean 2n times 2 times n minus 1 times 2 times n minus 2. See the pattern that has to develop? And if we let n equal 5, substituting 5n for all those n's, we get 10, 8, 6. So you can see where we're going with that. So as n goes to infinity, this expression is going to be a product of positive even integers. So 2n factorial is going to cancel out even factors. Now let's think about 2n minus 1 factorial. That would mean 2n minus 1 times, now let's remember, we subtract 1 from the n. So that's 2 times n minus 1 times 2 times n minus 2 minus 1 times 2 times n minus 3 minus 1, so forth. That would make this 2n minus 1. 2n minus 2 minus 1 is 2n minus 3. This is 2n minus 4 minus 1, 2n minus 5. This will become 2n minus 7, and so forth. So if we let n equal 5, then the 2n minus 1 factorial is going to be 9, 7, 5, 3, 1. So we're looking at odd factors there. We need to consider 2 to the n. Again, when n is 5, I have 2 to the 5th. Now, the answer that you get in the text is this one right here. This actually came from this. There's your -1 to the n minus 1, divide by. Remember, 2n factorial gave us even factors. Divided by, we know that n factorial, 10 times 9 times 8 times 7. And then this random 2 to the n thing. Where in the heck? Why would that give me, what's going to go on here? 2n factorial is going to cancel out the even factors from n factorial, leaving only the odds. But there's a little bit more. If I take, let n equal 5, using this right here, I get -1 to the 4th times 2 to the 5th times 5 factorial over 2 times 5 factorial. Now we know that 2 to the 5th is 32. 5 factorial is 5, 4, 3, 2, 1. 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So the 5, 4, 3, 2, 1s cancel. And then what we have here is, let me see, I can cancel the 8, leaves 4. And let's think about this. I have 4 over 10 times 9 times 7 times 6. Okay, 2 of that can go into this, leaving a 5. And the other factor of 2 can go into this, leaving 3. So what I get is 1 over 3 times 5 times 7 times 9. And this is just for when n is 5. So you can see if we let n go to infinity, I'm going to get the pattern I need. And that is your nth term. Now, this is a lot of wave your hands magic. Never would I give you one like this. I don't know why. All of a sudden, they put this ridiculously hard one in the book, but I do think it's interesting because I want you to see that you can have a series made out of a lot of different expressions. Look at what this one has. This has an exponential function, and it has factorials, and it has a modified factorial. So there's a lot going on, and that's what you need to really get out of this. There's a lot that can go on, creating our very, very interesting sequence of terms. And that concludes section 9.1.